Well, hello everybody. We are back to that Fender Champ Model 5 F1 schematic because today is the day to talk about the triode. So this is the that tube, the 12AX7. This is triode 1, triode 2, all in the same package. And here it's used as a two-stage preamp. So input, output becomes input, and input becomes output to the next stage. And what I'm going to talk today, what I'm going to talk about today is the triode operation, the general triode operation as an amplifier. And I'm going to talk about this thing, the bias. So this is the cathode bias. There are other ways of biasing, but I'm going to talk about the cathode bias because that's what is used here, also on the 6v6. Okay, so let's get right to it with some nice, albeit a little bit ugly pictures. Okay, I know it's a bit, there's a lot of information here. Cocos. So this is the triode, and this is my triode circuit. So this is your triode, typical triode. So of course it helps if it's connected. So this is your plate at the top. So it's typically the positive side. This is what's called the control grid. And this is your cathode. And this is your load resistance. So this is where you're going to develop the output voltage. Here, this is my EBB or the B+, whatever you call it. So this is to make sure that the triode is going to operate properly by feeding quite a large positive DC on the plate side. Okay, so this is the grid, as I said. This is okay. So here I'm going to talk first about the fixed bias before talking about the cathode bias. So this is a bias obtained through a battery. So this is ground at the bottom. So this is the plus of the battery, plus, minus. And this is my signal. So this is my AC signal. So for instance, a signal coming from your guitar or whatever. Okay, so you have your bias battery here. So that's going to be, let's say, I don't know, minus 3 volts. So minus 3 here. Let's say minus 3 volts. Then you have the signal here. So of course, this is there's a connection here. So it's like this, and here you have something here, an AC signal in series with this. So when you look at the total grid to cathode voltage, so total the voltage from here to here, you get the signal, but you also have the bias battery, the DC voltage, which is here. So this is the minus 3 from here. Okay. So the total grid to cathode voltage, it's not centered on 0, it's centered on the bias here coming from that battery. Yeah, so this is your the DC part is the bias voltage, so the minus 3, and then you have your AC riding here. So, but the important take here is that the bias voltage, the DC voltage, should be negative. I mean, sufficiently negative so that you don't have swing that go over the 0 reference point. And the reason why the DC bias voltage is always negative is because you don't want grid current. And you don't want grid current because it causes distortion. So in tube circuits in general, you will always have negative bias. Okay, so always remember that it's always negative for the most part. It's very similar to NPN transistor, where you put the signal on the base, and this would be like the collector current. So because of this, then I'm gonna have to have another, hold on, I didn't do the plate current, but the plate current, okay, so that's your, let's just look at the signal. So it's on 0. Then you have the total grid to cathode voltage. So this is 0, but it's actually sitting here at the -3, the bias. So it's like this. So it's the same as this here. And then the plate current is probably going to be somewhere here. It's going to be like that. Okay, so this is the plate current. Similar to like the collector current. So from the plate current, okay, so this is the signal. This is the total grid to cathode voltage, and this is the plate current. So it's very similar to what you would see with a transistor, NPN transistor, signal at the base, and this would be your collector current. So let's go back. Okay. So the plate current, when it goes through that load, it produces a load voltage. That's the whole point of the whole thing. And of course, it's much higher, and it's in phase, by the way, with this one. And again, this is the 0. It's riding somewhere. It's riding on that DC voltage. So that's the DC load voltage. That's developed by the DC plate current. And if you look at the plate voltage, which is here, which is what we are interested in, because this is going to be the input to the next stage, the plate voltage looks like this. It's the same as this, but there is a phase inversion. And you might ask, how come there's a phase inversion? Well, it's very, very easy to see, because if you just do a Kirchhoff voltage law, Vp, so the Vp, which is here, Vp, is equal to EBB, or the B plus if you want, B plus, is equal to EBB minus VRL, this one, minus VRL. So because you have a minus here, it causes an inversion. It's as simple as that. That's why you have the inversion. It's because of this guy, the minus. Okay, so this is fixed bias. Let's look into the cathode bias. Cathode bias. So here you have the B plus again. So it has to be pretty high to make sure that the triode operates properly. This is your triode, plate, grid, cathode. This is the grid resistor. This is your cathode resistor. This is the cathode capacitor, also known as a bypass capacitor. And here I put the ground here, which is what usually happens. So the ground is here. Okay, so let me try to explain how that works. Actually, I'm just going to read what I said. So the DC plate current coming from B plus causes a voltage drop across RK. That we can all agree on that. There's a voltage drop, and it's the proper plus here, minus here. So Vk is greater than 0, and let's say it's 3 volts. Okay, so here you would have maybe Vk 3 volts. But so now we know the potential at the cathode, but what is the potential at the grid? Because as you know, we want Vg to be less than Vk. We want to have a negative bias. But we know that Vg equals 0 because there's no DC current, so there's no voltage drop here on that grid resistor. So no voltage drop because there's no grid DC current due to Vg being less than Vk. So you have Vg equals 0. So if you look at the voltage between the grid and the cathode, between the grid and the cathode, it's negative. Okay? Which is exactly what we want, negative bias. And you may wonder why we have CK. CK is there to keep the VK constant, because as soon as the AC signal comes in through the air in the plate current, if you don't have a CK, then the VK is not going to be stable. It's going to go up and down, which is not good. Unless you want that, you might want like a tremolo effect or something. But you want VK to be constant when the AC comes in. And the CK is basically bypassing the AC signal. So it's there to keep the VK constant. And if the VK is constant, then the negative bias is going to be constant. So that's what we want. And it's called a bypass capacitor. Okay, so that's pretty much it about the triode. So I think I'm going to stop here.